tutorial, we'll learn how to use IIR filter, that means impulse infinite response filter, present inside the Sci-Compiler to emulate analog filter. IIR filter better represents than other kind of filter like finite impulse response, FIR filter, the analog behavior. Indeed, if we want to replicate, for example, a semi-Gaussian shaper, the best choice is to use this kind of filter. Sci-Compiler in the menu DSP has different kind of IIR filter. We have Butterworth, Bessel, Chebyshev, elliptic, notch resonant filter. And for Butterworth and Bessel are available both first order and second order filter. The filter difference is between the response in pass band and the stop band. Some filter like Butterworth has better flat response in pass band. Other filter has a higher sharp transition band like Chebyshev filter. Okay, now we want to implement, as I said, a emulation of a semi-Gaussian filter. So we can start from a Butterworth first order filter. I configured at high pass, we can set the cutoff frequency to 1 MHz, and we select int 17 because we want to be able to represent also negative number. And so we pick this filter, okay, and then we want to create also a low pass filter, a Gaussian filter as a high pass filter followed by multiple series of low pass filter. We can choose, for example, to put a second order Butterworth filter with a pass band of 50 kilohertz. Again, input data tape int 17 to have negative number, to be able to represent a negative number, and we can connect these two filters together. If we want to create an higher order filter, we can connect multiple low pass filter in cascade to this filter. Now we need a data source, so we can choose from input the analog in, and we choose analog 0, but because we are simulating design, it's not important which input we choose, because we just right click here and choose add edit to simulation stimulus. And now we can configure the generator to generate exponential signal like here. So here we select exponential signal in under mode signal generator. I choose to generate 10,000 points for each exponential, repeat it 3 times, and have a decay time of half microseconds, and an amplitude of 1000. I just press generate, okay, and I connect together. Okay, you see that see in original sites it's 16, destination is 17. Yes, because this works in integer while this is working as unsigned. We need to move the filter, the blocks away, and then use MISC unsigned to signed, and choose that we want to start from an unsigned 16 bits and convert to signed 17 bit. Okay, and now we can place this here. So we convert the number in signed, and now we can output on probe because we are simulating. So we can go under simulation menu, select insert probe, and we can say probe HE, and we see the signal in the middle with AC coupling signal, okay, here. And then we make another probe filter out. Okay, and we can take this, put 30 here. Okay, simulation, we need to drive the reset. Otherwise, we can get unknown number because the simulation cannot propagate random number. But when the number is not defined at the beginning, it's signed it as unknown. So we need to go to the toolbar, timer encounter, choose timer, enable. Now we create a constant as a target here. 10 is more than enough, so we can get a reset signal. Running can be the reset signal for 10 clock cycles. So we are sure that the filter will be reset and we will not have unknown numbers. Now we can run the simulation. Okay, it started. If you look at here at the beginning, you can see that Sci-Compiler invoked Python to generate the coefficient. You can see that the coefficient generated is much more than 1. The b is the denominator of the transfer function of the filter. So it generates several coefficients for the numerator, more than what we expect, and also for the denominator. This is because we are using a technique that is called scatter and look ahead to generate pipelining filter in FPGA. Everything is explained in the user guide. But in synthesis, the idea is that we can move to higher order the singularities of the filter, and so we convert the second order filter in a sixth order filter, where the first and the second order and the fourth and the fifth order pole are not present in the transfer function. So we can introduce a pipeline, and so we can have a filter that runs at high speed inside the FPGA. Okay, now we run simulation. We can press view waveform result. It opens the viewer. Okay, under test bench, we can pick 80, probe AC, probe filter out, and we can insert everything here. Zoom out. Okay, so now they are number. We want to see a graphical representation, so we select everything and choose data format signed decimal. Then we can again go here, analog, and select step. Okay, we see something. We can see better by inserting analog spacers somewhere in the design. Analog spacer again. Okay, now we can zoom. Okay, so zoom here. Okay, you can see the input signal, the exponential, the AC coupled, so the AC output filter, the first filter, and the low pass filter that is similar to the output of a semi-Gaussian chip. If you increase the order, you can so if you increase the number of blocks in the chain, you can get better filtering field. Thank you.